Okay, this is our data set. We have three variables: family size, income, and amount spent. So our problem statement would be to predict amount spent based on family size and income. So we'll have to create an equation that relates amount spent to family size and income. So family size and income are our independent variables, and amount spent would be our dependent variable. So first let's understand the relation between family size and amount spent and income and amount spent. So let's plot a chart between family size and amount spent. Insert a scatter plot. Okay, now let's take a look at this data. There seem to be a number of families with family size 2 whose spending far exceeds 3000. While surprisingly for family size 5, there is no spending above 3000, it's all below 3000 only. So looking at this, we can conclude that there is no linear relationship between family size and amount spent. Okay, so let's take a look at the relation between income and amount spent now. Okay, now this is the income and this is the amount spent. So here we can see that there is a clear relationship. As the income increases, the amount spent also seems to be increasing. But is this relationship truly linear? We'll have to wait and watch. We'll come back to this part. Okay, for now, we have inferred that there is no relationship between family size and amount spent, and there is a relationship between income and amount spent. So let's do one thing, let's determine the correlation also. So to find the correlation, go to data, data analysis, select correlation, choose the input range, which would be the 3 columns here. Now click on labels in the first row, new worksheet, okay. Okay, it gives the correlation coefficient by measuring the correlation between the 3 variables. So if you remember, correlation coefficient indicates the strength of a linear relationship between 2 variables. So between amount spent and family size. So between amount spent and family size, the correlation coefficient is minus 0.13, a weak negative correlation. Between income and amount spent, it is 0.74, a high degree of positive correlation, which we kind of expected by looking at the graphs initially. And also, the correlation coefficient between income and family size, the 2 independent variables, is 0.02, a very weak positive correlation. So this indicates that there is no multicollinearity. Let's perform the regression now. Go to data, data analysis, choose regression. The input Y range, it should be the amount spent. X range would be the family size and income. Labels here, and choose residual plots alone here. Okay, this is our regression output. So what is my regression equation based on which I can predict Y for future X values? This is how you build it. Your amount spent is equal to the intercept 395.571 minus 129.415 into family size plus 0.0174 into income. Yeah, this is how you build an equation. So if you substitute income and family size in this equation, you can predict the amount spent. But is this equation accurate? How do I evaluate this model? These are some ways of evaluating the model performance for regression. First one, coefficient of determination. So the one we saw earlier was coefficient of correlation. This is coefficient of determination. It is the proportion of variation in dependent variable that can be explained by the independent variables. This is the value in our example. It is 0.58. It means 58% of variation in amount spent can be explained by family size and income. So to put it more clearly, there are many factors which contribute to different amounts spent for different families. But if we have the knowledge of family size and income alone, we are able to explain 58% of the reasons for the variations in amount spent between different families. It is denoted by R square. It ranges from 0 to 1. A high R square indicates a reliable model for prediction. So a value of 0.7 or higher is generally considered good enough. Our case has 0.58 only, which is not sufficient to produce a reasonably accurate prediction. The next measure is adjusted R square. So it is a modified version of R square that has been adjusted for the number of predictors in the model. It increases only if new term improves the model more than you would expect by chance. Meaning, if you keep adding more and more predictors to your model, you will generally see an increase in R square. This could just be a chance increase rather than a real relationship. So adjusted R square accounts for this. You won't see adjusted R square increasing by much when you add more and more predictors which have no real relationship to the dependent variable. It is generally recommended to look at adjusted R square instead of R square to determine model performance, specifically in cases where the number of predictors are very high. So here we are going to go with 0.579. The next one, significance F. The F value tests the significance of the overall model. So this is the same F test which we have seen earlier. Here it tests to establish if at least one regression coefficient is not equal to 0. That is, it compares the intercept only model to the actual model. So let's take our case. In our case, it compares these two models. The intercept only model is denoted by y equal to 395. The actual model is denoted by y equal to 395 minus 129 into family size plus 0.017 into income. So it compares the predictions generated by these two models. If it doesn't find any significant difference between these two predictions, the significance F value will be greater than 0.05, which will indicate that the coefficients are 0 or the predictors chosen don't really have any predictive power. So in our case, we find this value is 2.97 into e power minus 38, which is very much less than 0.05, and so we say our model is significant. Okay, the next measure, p-value. P-value for each of the coefficients show the significance of the coefficient at 95% confidence level. So small p-value shows the coefficient is unlikely to be 0, meaning this predictor is significant. So we see both our predictors have a p-value of less than 0.05, hence both are significant. Okay, now we have a significant model with significant predictors, but still our R square is only 0.58. So we would need to identify more variables that could impact the amount spent and then include them in the model. So that is how we'll improve the model performance. But now we have only two predictors. Let's see if we can improve the model performance by some other means. So let's go back to the assumptions of linear regression. The variance of residuals is constant. So it means there is no pattern in the residual plot, or the data distribution in the residual plot is random. So this is our residual plot. So let us focus on the income residual plot. So we see that the residuals increase on both sides of the zero line as income increases. So this could be an evidence of a non-linear relationship between income and amount spent. So in case you are wondering what is residual, it is a difference between the actual and predicted value. So you can see the residual and predicted value for all records here. And note that the sum of residuals is always close to 0. So now we can improve the performance of a model by accounting for non-linear relationships, if any. So before going into that, let us look into a couple of ways by which we can improve the performance of a regression model. So the first method is transformation of variables to account for non-linear relationships. The second one, addition of interaction variables. Okay, how do you transform the variables? So you either take a natural logarithm of x or a natural logarithm of y or square root of x or square root of y and include this field in the model building. So how will you know when to choose which transformation? So you need to look at the plot of x versus y and find out how it looks like. So this is how y equal to ln x looks like. So if you find the plot of your x and y looking like this, you have to take a natural log of y to convert it into a linear relationship. So similarly, take a look at other graphs. So you will find that these four transformations cover most of the cases. So there is something called interaction variable, which is not suitable for this example. We'll discuss it in the next example. For this case, let's go back to our plot of income versus amount spent. So probably it looks like a y equal to ln x curve. So let's try to match it to that. So I would need to take a natural log of y to make the curve linear. So my equation now would be ln of amount spent is equal to b0 plus b1 into family size plus b2 into income. So I will now create a new column, ln meaning the natural logarithm, ln of amount spent. So I will write my formula for this. Okay, so this is our new column, the ln of amount spent. Now we'll run a regression now with the dependent variable being ln of amount spent. Same procedure, data analysis. Regression. So y range this time would be ln of amount spent. X would be family size and income as usual. Labels, schedule plots. Okay. This is a regression output. So you can see there is a significant improvement in the R square value. It's 0.65 now. So as before, we have significant F values and significant P values, which indicates the independent variables are significant and the model is also significant. And unlike the earlier case, the income residual plot seems to be randomly scattered. There is no pattern visible in this plot. So this means we have ensured the assumption of homoscedasticity or constant variance of residuals. So only if this assumption is satisfied, the regression equation can be relied upon. Okay, now how do you predict the amount spent now using this regression output? So it will be ln of amount spent is equal to 6.1 minus 0.16 into family size plus 1.66 into e power minus 5 into income. So using this equation, you will get the ln of amount spent, and then from there you can get the amount spent value. Okay. So we are done with this problem. In the next video, we look at another regression problem.